Okay, so today we're going to look at how things behave in a vacuum. So again, like certain planets like Mercury and our moon and the planet Mars, they have very little or no air pressure. So how would things behave different? How will the balloon behave in a vacuum? And we're so used to having this air around us. All around us we have this air, and again the air is particles moving. Particles moving will collide with things. If particles move and collide with things, that'll cause a force. So like if your arm is just sticking out here, there's air particles hitting you and crushing on you, and kind of there's a crush, a squeeze on you from all sides from the air. Well, what if I took that away? What if there's no longer any air hitting you? Like this balloon, there's air inside pushing out and the atmosphere pushing in, so it has this constant size. But what if there's no longer any air on the outside? Well, that's what happens in here. If I put something in here and I turn it on, it'll suck the air out and it'll be a vacuum. So it'll simulate the surface of the moon or Mercury or Mars, or just outer space in general. Okay, so first of all, let me just show you what a vacuum looks like, just to show you how it, well, it doesn't look like anything. But so I'll turn the pump on, and it's just sucking the air out. So whatever, just sucking the air out of this tube here, sucking the air out of this hole in the bottom. Okay, so there's a vacuum inside. Notice it doesn't look any different. It looks the same as before. It's really, you can't see the air particles in the first place, so how can you see if they're gone? Okay, but this is interesting. What the? This big, solid, heavy base, it's about 5 or 10 pounds probably, it sticks to it. What the heck? It's sticking to it. And even though I'm a pretty buff guy, I got some pretty big pipes here, I can't pull that sucker off of there. And even like Arnold Schwarzenegger couldn't pull this off. Some big, huge bodybuilder couldn't pull this thing off of there. It's stuck. Did I put glue in it? No, there's no glue in it. It's using the power of the atmosphere. This shows you how much crushing the atmosphere is on you. We're used to it, so we don't notice it. But right now, there's zero pressure inside pushing back. There's just no air pushing back, but you still have the atmospheric pressure of one atmosphere pushing down, and also on the bottom pushing up. So it's like it's being sandwiched between one atmosphere of pressure. And there's nothing inside pushing back. So right now, all you have is the atmosphere crushing, which is the same crush that's on you. So again, I can't pull this off. Once I put the air back in, so if I open this little valve, you can hear how much it's going to suck air back in. That's how much air. It's repopulating the air. Now with my fingertips, I can move it now. So now there's air slamming on top, air pushing at the bottom, but there's also air inside pushing around. So now all I have to do is fight gravity now. Before I had to fight gravity and one atmosphere of air pressure. Now I just can fight one gravity of gravity. It's pretty easy. Okay, let's put something in it. That was kind of boring. Let's put some stuff in there now. To prevent things from getting sucked down this little hole here, I need to make sure I put a screen in there, though, otherwise things will get pulled in. So again, like I said, this balloon right now, the balloon has air inside pushing around. There's air inside pushing out on the balloon, but there's also air on the outside pushing in on the balloon, so it has this nice constant size. But if I took this to the moon or Mars or something, this will happen to it. Make sure the screen's out of the way. Again, the screen is just there to keep it from sucking down into the hole, which will cause problems. So, okay, so shut that. Turn it on. You're going to see it get bigger. Yeah, it's going to pop. It's going to be super loud. Okay. So that wasn't loud at all. Let's put the air back in. So without the air crushing down, the balloon could expand as much as it wanted until eventually it just tore the sides open. There's a bunch of fragments of balloon scuzz in here now. I'll get that out of there. Oops. Let's see how I'll get the. Here's the balloon now. Let's get that all out of there. So again, if you had a balloon on the moon, or Mercury or whatever, the balloon would just pop. So, same with your lungs. You have air in your lungs. You can't just like hold your, say if I stepped outside my moon colony, I forgot my spacesuit. Oops, I forgot my spacesuit again. Silly me. And I stepped outside, you couldn't just like hold the air in your lungs. The air, without the air pressure pushing back in, the air in your lungs would come out and your lungs would evacuate. You'd suffocate very, very rapidly. So, okay, so that's a problem on the moon. So that's why they have to have, those spacesuits they have are like a bubble of air around you that can't pop. it's, it's made so it can't pop. So you have this bubble of air around you so you can stay alive. Okay, so that's one thing. Gas volumes will expand. So again, the air in your lungs would want to expand. But another thing that's interesting is water behaves differently. So here we have this water, this regular, just put some water from the sink in there. And right now it's not boiling. It's not 100 degrees, it's not boiling. If I take the temperature just as for curiosity, it'll relate to something we're going to do later. I'm just going to take the temperature of it. So it's about 20 degrees Celsius. So trust me on that, 20 degrees Celsius, which is basically room temperature. But now, right now, the atmosphere is like pushing down on the water. So again, the same squeeze that's squeezing on you, the air colliding with you in all directions, it's also in there colliding with the surface of the water, pushing the water down. So the water can't like leave, the water can't break apart from each other very well. But if I put it in a vacuum, without the pressure crushing down it, the water can leave more easily. So give it a couple seconds here. And it's starting to bubble a little bit. And it's bubbling, and it's actually boiling. It's a full boil right now. This is not hot. Big thing. You guys are used to at home, you're used to boiling water with heat. This is not hot. This is still a room, look here, I can feel it's room temperature. It's not hot. There's not no Bunsen burner underneath it. It's boiling by changing the atmospheric pressure. At home, when you cook noodles, you boil by adding more heat. This is boiling with decreased air pressure. So on the surface of the moon or Mercury or whatever, outer space, water boils. Here's a problem though. Your skin is mostly water. We're just big bags of water. If you're a big bag of water and you don't have the air pressure squeezing on you, the water is going to leave. You'll start desiccating. You're going to start drying out. So without the air pressure squeezing on us, we can't hold water. You can't have a swimming pool on the moon because it would all boil away. So let's just, I'll show how it's boiling again. So it's boiling. The second I put the air back in, once this air pressure comes crushing down on it again, it stops boiling. Okay, so I boil the water. Now again, let's just prove this is, normally you think, oh, water boils at 100 degrees. This isn't possible because I'm super manly or something. It's still like room temperature. Actually, let's check the temperature. Just to prove to you it's not, it's not, so it's 20 degrees before. It's about 18 degrees now. What? It's 2 degrees colder. It actually got 2 degrees colder. Well, the principle there is that, in any kind of a volume of water, there's always hot particles and cold particles, like hot and cold particles together. Well, when the pressure's lower, what's the easiest one to leave? What's the first one to leave? The cold particles. So basically, temperature is an average of all the particles, temperature of the particles in there. So if the pressure is low enough, the hot ones, the hot ones leave first. The hot ones leave first, leaving behind the colder ones. So the colder ones left behind is 2 degrees colder than before. So I actually boiled the water, and it got colder. On your stove at home, you add heat and make it 100 degrees, you're making it hotter to boil it. So there's 2 ways of boiling water. Kind of interesting. Okay, so those are the general principles I wanted to go through. Another thing is sound in space. So let's just quick show that balloon again. So you notice when that balloon popped, it did make a big boom. If I pop a balloon, it makes a bigger, louder noise. In here, the balloon is very, very quiet. Just turn it on there. So it made a little plip, but it wasn't like a big boom. It was quieter. So that's because sound doesn't travel in a vacuum. Sound doesn't travel in space. One of the taglines from the 1978 movie, I think it was, Alien, the movie poster for the movie Alien was, "In space, no one can hear you scream," which they can't, so I guess that's actually accurate scientifically. Movie title there, movie tagline. So when it popped, there was still some air there. It wasn't a full vacuum. So it still made a little clip because there was a partial vacuum. It was just a partial vacuum. It didn't get down pressure low enough. But if it was a perfect vacuum in there, it would have just been, it wouldn't have been like any plipper, but it would have been perfectly quiet. So you need sound, like when you speak. So like say if I'm speaking here, your vocal cords vibrate. When your vocal cords vibrate, that pushes air particles, then this air particle bumps into that air particle, which then bumps into the next air particle. It's like a chain reaction of when your vocal cords vibrate, it hits particle to particle to particle to particle. That then goes in your ear, and then those vibrations hit your ear like a little drum, and you can hear sounds. In space, there's no air. So if I was on the moon with my fellow astronauts, and I took my helmet off to say, hey Bob, come over here, I'd be like, you know, even if your vocal cords vibrate, there's no air to push on, so there's no air to move between. So light can go through a vacuum. Notice you can still see through there. When light goes through a vacuum, which, you know, from the sun to the earth, that's good, because light goes from the light and the infrared and all that stuff from the sun gets to the earth, but sound doesn't go through space. Okay, so if you had a Star Wars battle, you watch Star Wars, Star Trek, you have these battles, this big, huge, you know, whatever TIE fighters and all these, you know, whatever Star Destroyers are like, all this stuff. Here's a real battle in space. Yeah, you'd see the light, you'd see like the big, huge highliner, like, you know, exploding, but you wouldn't hear the sound. It'd just be, but you'd see like the flash of light and stuff. So sound doesn't work in space. So that's a long way of explaining why this balloon didn't make a big boom, it just made a little blip. Okay, so that's the general scientific ideas. Let's just do some fun stuff now. Let's just kind of go through and look at some weird things. So like this, just to kind of show how skin would lose, you know, with your water in your body, skin would lose its water in a vacuum. I have an apple. I'm just going to take this apple and cut it. And this would be a good demonstration of how skin works. So again, like right now, the apple, there's air pressure squeezing on the water, so it works just fine. If I put it in here and take the air away, the water can leave better, more easily. So you can see some sort of steam kind of coming off it, and I'm not sure if this is visible. You can probably see some water bubbling off of there. Little bubbles. Yeah, I can see it bubbling. That would be your skin. Little bubbles everywhere. Not super visible, but I can see it pretty well. So you can sort of see it. Little bubbles everywhere. That would be your skin. Literally, your skin would be bubbling like that. You'd have the bubbles just kind of with all the air pressure squeezing on you. Yeah, it's almost done bubbling now. So technically, this apple's desiccating. The apple's losing moisture. So it's like kind of like the freeze-dry process, but if I put the air pressure back in again, it kind of stops it. So this apple should be this little wedge apple should be a little bit lighter than before. Lost a little bit of water. Okay. Now a couple of more fun things, and things that have like marshmallows and stuff. Anything that has a gas volume will look pretty cool in a vacuum. So I have a couple marshmallows here. So marshmallows. Marshmallows are basically just balloons, but instead of having one large air chasm, it has millions of tiny little air. These are jet puffed corporation marshmallows, and jet puff means that it's like they force air into this sugar mixture, and it puffs out. So I'm going to put these marshmallows here again. So this is just like that balloon. There's air bubbles, there's air pushing out, but there's also the atmospheric pressure squeezing down on it. So they have a certain size. But if I take away the air on the outside, they'll start expanding. So I'll put a marshmallow next to it so you can see the regular size versus the expanded size. So it's going to start expanding. There's less pressure crushing on them. But like the balloons, oh, they start popping. They're popping, pop, little pops everywhere. So it got bigger for a while, then it contracted back down again. And now it kind of looks like normal. It's kind of like the same size as before. But they lack air, like the popped balloon. Here's the popped balloon. Like the popped balloon, the bubbles pop. So when I put the air back, it's going to be kind of funny. They're now just like sugar shells without their air inside. So here's the general idea there. That They're both, you know, they both have this, they're both about the same weight. I mean, they both have the same sugar. It didn't change the sugar and the gelatin. It's all the same. You know, this had like 2 calories. This is now still 2 calories. If this causes cancer, this also causes cancer, whatever. You know, they're all the same. It's just that there's just less air, like the balloon that they popped. So anything that has air in it, this will work with. So in outer space, anything that's a liquid, the liquids will start boiling, and gases will, you know, expand. Solids don't make a difference. Notice, like all this plastic and this rubber gasket here and the metal and stuff, nothing changed there. It doesn't change solids. It's just liquids and gases change. Liquids boil and gases expand. So let's put a couple more fun things in there. We'll try a bunch of, it's Easter time pretty soon here, so we got some fun little, you know, Easter snacks and stuff. Got some marshmallow eggs, and of course gotta have peeps and stuff. Let's kill some peeps. I'll put a Twinkie in there just for now, just to see what that looks like. So the Twinkie, now careful, the Twinkie, there's cake and filling. Cake and filling, they're both different there. The cake and the filling both have a different, you know, the cake is very porous, so air can get in and out of there really easily, so I don't want to change that. But the filling is just like the marshmallows, it's puffed, a bunch of puffed air and stuff. So turn that on. We'll see the filling expand. That's a good one. The filling's expanding, but the cake's not really changing at all. But like the marshmallow, it's losing its air. So there's this filling. It's a bunch of oils and sugar and whatever else. With the fluff air, now the air's gone. This is going to be this. I'll kind of pull this all back up there, but I'll open it up for you. So the sugar's still there. Again, it's just as bad for you as it was before. But inside now, instead of having a fluffy cream, it's just a slimy, whatever. It's the same oils and fats and sugars. It's not puffed anymore. And it tastes the same. You know, it's like the same, whatever. Still tastes horrible. So same as always. Okay, I got stuff all over me. Okay, a couple more fun filling things here. Gotta do a peep. It's Easter season here. I'll stick 2 peeps in there and see what happens. Just in case, I'll put it on top of that rack there. Oops. There. Okay, so let's kill some peeps. Again, just marshmallows. They'll expand. I'll put one next to it for comparison. So the sugar's cracked. Oh, but they're popping. All the bubbles are popping now. They only get to a certain size before the bubbles pop. So now we have these peeps that don't have as much air in them. So let's just see what they look like without air. You get roadkill peeps. Looks like a squirrel that's been squished and dried up on the side of the road. Tasty thought there. It's nice and kind of looks like a leathery peep or whatever. Again, same flavor, whatever, same calories. All we lost is air. We didn't lose any sugar or anything. That's all the same. Okay, 1 or 2 more. This is pretty fun. The marshmallow egg has a hard chocolate shell in it. Oops. Don't have one to compare to, but let's do that one. So the hard chocolate shell is going to be kind of fun when the marshmallow cracks it. Again, the chocolate won't change. It'll be pushed and broken by the marshmallow, but that's about it. Ooh, cracked inside. There we go, it's just falling apart there. It's real big. But eventually, they'll start popping. Okay, they're starting to pop now. Pop. They're popping, okay, great. So now we have this marshmallow filling that doesn't have any fluff to it anymore. So just the marshmallow scuzz. Marshmallow. Slimy, whatever. It's just kind of hard. It's kind of hard now. It'd be chewier. It's like flattened out and stuff now. Instead of being, you know, it definitely has less volume than before. So if you eat that, it'd just be chewy instead of fluffy. Okay, 2 more things here. This is always fun. This is a great one here. This is the Hostess snowball thing. Oh, that's purple, but the old snowball. Snowballs, again, they have the cake filling, which doesn't really change. But they have this, it's a cake filling with hemispherical, if you want to call it that, marshmallow coating around the outside. I'm going to put it upside down. So the marshmallow will expand. There's also cream filling inside that'll probably squirt out the top. So we're going to have cream filling squirt out the top. The marshmallow will expand, but then the cake won't do anything really. The cake is going to be about the same. But that's kind of fun when you put the gas back in. And all the gas is going to be gone. So there goes the cake. It's going to split away from a big mushroom. It's going to split away from the cake. Oh, but now it's popping again. So it's losing its volume. And the filling, you can't see it from this camera's perspective, but the filling is actually expanding in the bottom. The cake pushed up. So now I put the air pressure back in. Now the little marshmallow slash mushroom head is going to be smaller now. That one wasn't as impressive as usual. It did expand here, and the cream filling squirted out the side. But now the little top here is now smaller. So it shrunk down. Okay, one last one. This is always kind of fun. Some shaving cream. So this is standard shaving cream, Barbasol, whatever. I'm going to put a little bit in here. Wish I could take that out, probably. Just a little bit. Doesn't take very much. I calculated once. This has about a little bit more than 100 times increase in volume. So I don't want to put that. Actually might be too much even. I'm just going to put a little bit in there. Doesn't take too much. And we're going to, again, same things. Take the pressure out. Let the gas expand. Overflow the container. I put a little bit too much in. I'm careful not to overflow too much. Oh, geez. Okay, that's going to make a mess. All right. But then again, it's going to pop eventually. So you notice a little bit expanded a huge amount. It wasn't quite 100 times the volume that time, but okay. So that's about it now. It's all expanded, but now it's going to be this. Once it's over, instead of having fluffy shaving cream, it's just going to be like a slick, oily, slimy shaving cream. So it still smells like it, but it's just kind of this slimy, instead of being like a fluffy thing, it's just kind of a slimy, liquidy, whatever thing inside now, so kind of nasty. So, okay, so that's vacuum chamber demonstrations. So again, whatever happened in here would happen on the surface of the moon, or Mars, or Mercury, or Pluto, something without a gas. Venus, the opposite would happen. Venus has a higher pressure, so Venus would have a stronger crush. So these marshmallows would naturally be crushed down smaller on Venus. A balloon would be crushed down smaller on Venus with a higher pressure. So we just happen to have this nice 1 atmosphere pressure, 760 millimeters of mercury or 101.3 kilopascals atmospheric pressure. So that's good for us. So, all right, cool. Hope that was fun.